In this video, we're going to be exploring the properties of this point K here. So let me go ahead and go through how this point K is defined in the first place. We have our triangle ABC and our end circle with touching the sides at D, E, and F, and I is the center of the end circle. And the circle going through A, E, and F, and it also passes through I since angle AFI is angle AFE is 90 degrees. It intersects the circumcircle of ABC at point K, and that's how our point K is defined. And we're going to be exploring the special properties of this point in this video. So let's get started. So the first property that we're going to be listing is actually relating to the quite obvious one where K is the micro point of quadrilateral BFEC because the two lines intersect at point A here and we have AFE and ABC. If you haven't watched my video on the micro point, I'm linking it inside the description, so go watch it if you haven't already. Anyway, given this micro point here, it is particularly useful to go ahead and draw an EF, let it intersect BC at this point X. Then the micro point thing implies that KFBX is also cyclic. So we have this cyclic quadrilateral here. And we also have that, similarly, that KECX is cyclic. So something like that. And that's because the four circles meet at a common point. Now let's go ahead and discuss the next property of the point K. And to do this, we're going to be drawing in the circumcircle of triangle BIC. So we have it here, and it extends beyond. So yeah, and the two circles are tangent. They appear to be tangent, and indeed they are, because the center of the circle is the midpoint of IA, because it is the circle with diameter IA. While by the incenter excenter lemma, the center of this circle is just the midpoint of the arc, which lies on this line here. So thus the circles are tangent. So now we have three circles here. What can we do with them? Well, it seems obvious to apply the radical center theorem on them. And if we do this, we get that the line AK, so that's that, and then BC, because that's the other common chord, and then this tangent line here are concurrent. And this tangent line is none other than the line through I perpendicular to AI. So we have something like that. So if I go ahead and get rid of this circumcircle here in the diagram, we can actually rephrase it without the circumcircle. If AK intersects BC at this point L, then we have that AIL is 90 degrees. And that's the second property. The third configuration arises quite naturally if you constructed the center of the circumcircle of BIC, as stated earlier. And if we look at the diagram a bit more, we notice that KD and M appear to be collinear. So KD and M are collinear. This is our third property that we're going to be proving. So how do we prove it? Well, we have this point M introduced to us by the circumcircle of BIC by the last one, so it might help to draw that again. So we have BIC here. All right, so we have these random points K and D, and we not know how to relate them to the point M. So let's try taking an inversion about the circumcircle of BIC. So, and we're going to be determining where each point goes. So I gets fixed, B is fixed, C is fixed as normal. So let's see what happens to the other points. So the point A, let's first consider the circumcircle of ABC, which is the circumcircle of BMC. By inversion properties, this just inverts to the line BC. So BC and the circumcircle of ABC invert to each other. And this means that if I draw in the line AI and let it intersect the side at a point T, then T and A are inverses. And since I is fixed and the center lies on AI, the circle with diameter AI just inverts to the circle with diameter IT. So let me go ahead and draw that. All right. And as said earlier, the circumcircle of ABC inverts to the line BC. So therefore, the point K inverts to the second intersection of a circle with diameter IT with the line BC. But we all know that this is just the point the point D, sorry, because D is a foot of the altitude from I to BC. And so we get that K and D are inverses. And in particular, this implies that M, K, and D are collinear. So if I clear up the diagram a bit, so let me go ahead and erase things. We can actually rephrase this third property without the point M at all. So the line KD bisects angle BKC because it passes through the arc midpoint. And that's our third property. On the topic of inversion, let's see what happens if we invert about the incircle this time. So we have our incircle DEF. Let's see what happens if we invert with respect to that. So let's go ahead and draw things in. Then the point B gets sent to the midpoint of DF, obviously. And the point C gets here, and the point A gets here. So the circumcircle of ABC just inverts to the circumcircle of the triangle formed by the midpoints. But you should recognize the circumcircle of the triangle formed by the midpoints as a 9-point circle of triangle DEF. So it also passes through the other feet of the altitudes. Now let's see where the circumcircle of AFE goes. Well, that shouldn't be too hard because it's a circumcircle of IFE as well, and that inverts to the line FE. And since K is the second intersection of the circumcircle of AEF and ABC, it inverts to this point here. And therefore, if we go, let me go ahead and redraw D, E, and F, how to erase things. So if we construct the foot of the altitude, let's call it M, no, not M, P, then K, P, and I are collinear, and moreover, they are inverses with respect to the incircle. So K gets sent to P. And that's property number 4. We now present one final property before concluding our video, and it relates to our friend, once again, KD. So let's go ahead and draw that in. And suppose it intersects this circle here, and we want to deal with that because we have the circumcircle of AEF and it looks nicer. So suppose it intersects at a point V. Then let's see what's special about the line AV, because A is the other point and IV doesn't look that good. And we see that AV appears to be the altitude. So let's go ahead and extend AV. So let's go ahead and extend it to W. It appears that AW is perpendicular to BC. And so now let's prove this. So let's go ahead and redefine the point V prime. So V prime as the intersection of the altitude with this circle. And since angle AV prime I is 90 degrees, this point is therefore the foot of the altitude from I to AW. So, and we also note that D is here as the foot of the altitude from I to BC. So we have 2 feet of the altitudes. So this reminds us of Simpson lines right away. So we have to construct one last one before we can apply Simpson lines. So we want K to be the foot of the altitude from I to something. And this is indeed true if we take line AK, because angle IK is 90 degrees. So and now we have our friend here. And in this case, we called it L here. So that's L. Then I is the foot of the altitude from I to AL. So now we have 3 foot of the altitudes here, and we want to show that they are all collinear. And by Simpson lines, this is just equivalent to ALWI being cyclic. So let's prove this. So we don't have any other definition of W other than it being the foot of the altitude. So we have angle LWA is 90 degrees. So if only we could show that angle LIA is 90 degrees, we'd be set. But we know this is true from property number 2 that I stated in this video. And thus LWIA is cyclic, and we finish by Simpson line at I. So yeah, those are the several properties of this point K, and for some reason this point K is known as the A Sharky Devil point of triangle ABC in internet slang. And in the next video, we're going to be using these properties to solve a problem. So thank you so much for watching this video. Please subscribe if you'd like to